So this is chapter 10.6 in your textbooks. I don't think you'll need to reference the textbook at all. Dalton's Law of Partial Pressure is pretty gosh darn easy. All right. There's a lot of words up here. Here's what Dalton says. Dalton says that when gases mix, they mix homogeneously. Think about that for a second. Breathe in nice and deep. Isn't it nice that the oxygen isn't like low on the ground and the nitrogen is above it and the carbon dioxide is above that? Isn't it nice that it mixes evenly? Okay, yeah. The whole reason why life here on Earth actually works and we can breathe, every single one of us, is because gases mix homogeneously. Okay, they don't separate out. Okay, that's the whole idea behind that first statement. Okay, the second statement here is this: the idea of how much pressure you're under. You guys realize right now you're under 14.7 pounds per square inch of pressure. Possibly more because we just had a storm come. Oh, possibly less because the storm is gone. Right, when the storm comes through, the front of it is a high pressure wave, and the back of it is a low pressure wave. We might be at 14.6 right now. All right. Okay. But the whole idea is this: the pressure due to oxygen plus the pressure due to carbon dioxide plus the pressure due to nitrogen gas plus the pressure due to humidity equals 14.7 psi. Is there any complex math there? The sum of the pressures is equal to the total of the pressures. It's kind of a no-brainer, but it's nice to say. All right, and that's what Dalton's Law talks about there. All right. He also says that each gas sample has its own individual partial pressure, and that those are going to be due to something called mole fractions. So the fraction that is due to oxygen is due simply because there are a certain number of moles that is proportional to the pressure. All right. So mathematically speaking, the second bullet on that previous slide, pressure total is equal to pressure 1 plus pressure 2 plus pressure 3 plus pressure 4, ellipse. How many pressures do we have in the system? Okay. With the air that we breathe, there's nitrogen, oxygen, carbon dioxide, water vapor. And then there's a fifth component that basically we talk about that's a catch-all. It's all the rest of the gases, which usually is a little bit of xenon or neon or anything else that's a inert gas. Okay. Actually, I don't think there's much xenon hanging out that we breathe. I think it's more like krypton and argon and neon. All right. So there's something called a mole fraction. A mole fraction is kind of like a percentage. Mole fractions are represented by the symbol X with a subscript. You notice I've got a subscript A there. Usually you write down whatever the symbol is for the element you're talking about. So if I was talking about the mole fraction of oxygen, I'd write X with an O2 subscript. Okay. If I was talking about the mole fraction of argon, I'd write down X with a subscript of AR. Okay. It winds up being a dimensionless quantity that expresses the ratio of the number of moles of one component to the number of moles of all of the components present. And here's what that looks like. Okay. So right here, we've got mole fraction, which is sometimes what we're asked to calculate. What is the mole fraction of? And basically what we have to do here, I should have put this in terms of A. This is X of A, right? It's the mole fraction of A. This should be the number of moles of A over the total number of moles. Does this make sense to you guys? We're talking about a proportion here. It's kind of like a percentage, because a percentage is calculated as the total, the number of things over the total number of things times 100. The only thing about mole fractions is we don't times them by 100, so they're not actually a percentage. They're just a ratio. So notice there's a second way to get mole fractions. Mole fractions can also be calculated from pressure. Okay, so the pressure of the mole fraction of component 1 is due to the pressure of 1 over the total pressure. Sometimes you know how many moles of a gas total there are. Sometimes you know how much pressure total there is. Just depends on which one you have, whether which one's more useful. I'm going to put both questions up here. They're related to the setup here. They're both related to the same setup here. A mixture of gases contains 4.46 moles of neon, 0.74 moles of argon, and 2.15 moles of xenon. They're asking us first to calculate the mole fraction for each of the 3 gases, and then second to figure out what the partial pressure of each of the gases is if the total pressure is 2 atmospheres. So if I'm going to calculate the mole fractions, I need to know what the sum of the number of moles is. So I'm going to add up the 4.46, the 0.74, and the 2.15, and that gives me a total of, correct me if I'm wrong here, guys, 7.35 moles. Yeah? Okay. So if I'm going to calculate the mole fraction of, let's see, the first one's neon, capital N, lowercase e, that means that 7.35 moles goes on the bottom, and it looks like, according to the problem, 4.46 moles were present. Notice moles and moles cancel, which is why mole fractions are unitless. The calculator says 0.607, and I'm not going to have any units there. Okay. To get the mole fraction of argon, I'm going to do something similar. I'm going to put 7.35 on the bottom. I'm going to put 0.74 moles on top. Again, moles and moles cancel, so I've got a unitless answer here. We're getting 0.101, according to the calculator. And finally, for xenon, I'm sorry, not for xenon. Yeah, it is xenon, isn't it? Xe. We're going to do 7.35 on the bottom and 2.15 moles on top. Mole fraction, so the moles cancel. And I got 0.293. Again, unitless. It really bothers me to write unitless numbers, but I guess I can't do it here. Okay. If we're going to calculate the pressures in the second part, we need these mole fractions. Okay, so if I want to get the pressure of neon, and I'm hoping that this is going to make sense, there's 2 atmospheres total. 0.607 moles of neon is responsible for exactly 60.7% of this. All right, so what we're going to do here is we're going to take the 0.607 mole fraction, we're going to multiply it by the 2.00 ATMs. Unitless times units gives me units, so 0.607 times 2 gives me 1.21 atmospheres due to the neon gas. The pressure of argon is going to be 0.101 times 2.00 atmospheres again. And we're going to get, don't even need a calculator for this, 0.202 atmospheres were responsible from argon. And then the pressure of xenon should do something similar, 0.293 times 2.00 ATMs. And we should get 0.586 ATMs. Now, a clever individual could figure out a way to check their work here. So we should be able to add each of these partial pressures up, and the partial pressures should sum to the total pressure. So we should get 2.0 when we take 1.21, 0.202, and 0.586 and add them together. Will that always be perfect? No. We're rounding on each of these, so it might be plus or minus 200ths, 300ths, but we should get something pretty close. 1.998, so not bad, right?